Welcome to this video on the topic of givens rotations. Givens rotations are linear mappings that correspond to orthogonal matrices, and they can be used to create a zero at a single position in a matrix. And in this video I will show how you can choose givens rotations to get a matrix into upper triangular form, so we can use them as a tool to find a QR factorization of a matrix where Q is orthogonal and R is upper triangular. So let's look what we will see in this video. So I will give a definition for givens rotations. I will show some of their properties. Then I will explain how you can choose them in such a way that you can create zeros in a matrix. And I will also give an example of how this works for a 3 by 3 matrix. So let's see. First, you may have seen before household transformations. So household transformations can be used to create zeros. And with a household transformation, you can take a column of a matrix and create basically as many zeros as you want in that. So for instance, if you would like a matrix to be in upper triangular form, you can use one household transformation per column. So in general, you will have to create zeros in the first n-1 columns of a matrix, and you will need n-1 household transformations. Givens rotations require one rotation per element that you would like to be zero. So if you need to create, say, in the first column of a matrix zeros below the main diagonal, you would need n-1 givens rotations. So here is a little example. So here is a 3 by 3 matrix. So we can use one givens rotation to create a zero at the second row, first column. And we would need another one for the third row of the first column. And then we would need one givens rotation more to create a zero at this position here. So in the second column and then below the diagonal. So in general, if you have a larger matrix, you will require many more givens rotations than household transformations. So you may wonder when this is interesting. Well, it could be that you already have zeros in your matrix below the main diagonal, and then you want to transform it into upper triangular form. So for instance, you have an upper triangular matrix and one additional subdiagonal, and then you would require less givens rotation. So there it might be useful. Now, if we can do this, then basically we have found that the product G3, G2, G1 times A is upper triangular. So what we have left of the original matrix, that would be capital R, our upper triangular matrix. And then A itself is this product here times R, and this product we could call Q. And then we have found a QR factorization, because I will show that G3, G2, G1, all givens rotations are orthogonal, and a product of orthogonal matrices is also orthogonal. So how do these givens rotations look like? This is what I just told you. So you can define Q to be the product of these givens rotations, and Q is orthogonal, and A equals Q times R. So we have found a QR decomposition. So what does it look like? So if you see the definition here, then it's an n times n matrix. It is mostly the identity matrix because it has zeros. I didn't write them. It's mostly ones on the main diagonal, but there is one row P and one row Q. And then at column P and column Q, the entries are a little bit different. So on the main diagonal, we have C. And then off diagonal, we have S, and we have minus S. So you see that if you compute the inner product of any two columns, you find 0. And if you take the inner product of a column with itself and you use that C squared plus S squared equals 1, that every column has length 1. So the columns of this matrix form an orthonormal system. If you take two different columns, they're perpendicular, and the length of every column is 1. Now, of course, C and S are not arbitrary letters here, but you can think of them as a cosine and a sine. So what I just told you is G is mostly the identity matrix, except for rows and columns P and Q, and then GPP equals C, GQQ equals C, and the off-diagonal entries are S and minus S. So you can interpret G as a rotation matrix. It's a rotation in the PQ plane over an angle phi, and then C is the cosine of phi and S is the sine of phi. And G is orthogonal, since if you compute G transpose times G, you will find the identity matrix. So G transpose is the inverse of G. Now the next question is, we want to use these givens rotations to create zeros. How can we do that? So let's take a matrix A, which is square. Let's split it into its n columns. And first we start working on the first column. So I'm going to take U equals A1 is just the first column of the matrix, and all these entries can be non-zero, so I just gave them names. And I'm going to use a givens rotation G1 to get to V, and for V the requirement is that I would like to have a 0 here, and I'm not going to touch all these entries, so they just stay the same, but V needs to have the same length as U, because it's an orthogonal transformation that preserves the 2 norm, that preserves the normal Euclidean length. So that means that basically if I make this one 0, that bit of length needs to go somewhere, so I add that here to the diagonal entry, and that's going to become alpha. So the requirement that they have the same length gives that alpha should be the square root of A11 squared plus A21 squared. And this basically defines the givens rotation. So for the givens rotation, we are going to have the identity matrix for anything but the first and second row. The top bit, the top left bit, is going to be CS minus SC, and I'm going to choose them in such a way that if I multiply G1 and U, that I find V, and that gives me these equations here for the C and for the S. So I have two unknowns, C and S, and I have two equations, so I can solve these. And here I've actually done that, but it's simple. You can multiply the first equation with A11, like I wrote here, the second with A21. You can add them together, and you can use the definition of alpha basically, and then we have the boxed formula for C, and then we can use one of the other equations to have S. So from this you can compute C and S. I will do a little numerical examples with actual numbers in a bit. So after we have done that, so after the first step, what we are going to do is create an additional 0. So the new givens rotation G2 should create a 0 at the third position. And since it needs to preserve length, also we're going to change the first entry again. So to transform the first column, in general you need n-1 givens rotation, because we need to create a 0 here and here and here all the way down. So I'm going to need n-1 givens rotations. For column number 2, I'm going to need n-2 givens rotations. So in general, if all the entries are non-zero, you will need a half times n-1 givens rotations to get a matrix into upper triangular form. So let's look at an example. So here I have the matrix with columns. The first column is 1, 2, 3, the second column 1, 1, 2, and the last column minus 1, 0, 3. And I am going to try and transform this into upper triangular form using givens rotations. So let's see. The first step is to take the first column, so that's 1, 2, 3, and I would like to have a givens rotation G1 that transforms it into, well, I want a 0 here, I don't want to touch the last component, and I need to preserve length, and if you want to preserve length, it means that this thing should be the square root of 5, because then these two vectors have the same length. Now G1 should be of the form C as 0 minus S C 0, 0, 0, 1. And then if I do, so this is G1, if I do G1 times 1, 2, 3, I would like to find square root of 5, 0, and 1. So if I write it out, then I find that C plus 2S should equal square root of 5. Minus S plus 2C should equal 0. And the last equation tells me that 3 equals 3, and that is true. So what we have is that apparently C is 1 over square root of 5, and S equals 2 times C, which is 2 over square root of 5. So let's go to a new slide. So what we have found is that our G1 matrix, so the first givens rotation, is 1 over square root of 5, 2 over square root of 5, 0, minus 2 over square root of 5, 1 over square root of 5, 0, 0, 0, 1. So apparently this is an orthogonal matrix. So if you would do G1 transpose times G1, you would find the identity matrix. A is the matrix 1, 2, 3, 1, 1, 2, minus 1, 0, 3. And as I stated before, when you are working with orthogonal matrices, because the columns have length 1, you tend to have all these ugly square roots in there. Now, if you multiply these two, so if you compute G1 times A, you get the matrix, well, the first column we already know, square root of 5, 0, 3, that's basically by construction. Then we get for the second column, if you compute this, 3 over square root of 5 minus 1 over square root of 5 and 2. I have these on a bit of scratch paper. I don't do this by hand so fast. Minus 1 over square root of 5 and 2 over square root of 5 and 3. Of course, the last row is not changed, basically because G1 doesn't touch the third component of vectors. So the next step, step 2 of our givens rotations and how to choose them, is that we again look at the first column, square root of 5, 0, 3 it has become now, and we would like to transform that into something that has 2 zeros. So that means that the first component should by construction be equal to square root of 14, because we need to preserve length. G2 is an orthogonal transformation, it preserves length in the 2 norm, so these two vectors should have the same length. Now, G2 now has the form, it doesn't change the second entry, so it is a rotation in the 1, 3 plane. So the second row becomes 0, 1, 0, and here we get minus S, 0, and C. And you can probably guess how we are going to choose it. So the C and S, so they are different C and S now, right, than from before. They are chosen in such a way that if you would multiply G2 with this vector that we had, and then we would like it to be this vector, then again you find equations for C and S, and if you compute them, I have done that, you find C is the square root of 5 over 14, square root of 14, sorry, and S equals 3 over the square root of 14. So note that C squared is 5 over 14, S squared is 9 over 14, so together they're 1, as it should be. And then you can form G2, and you can also compute G2, G1 times A. And if you do that, so the first column we know, square root of 14, 0, 0. The second column becomes 9 over square root of 14 minus 1 over square root of 5, 1 over square root of 70. You realize why you normally would want to do this on a computer. And the last column is 8 over square root of 14, then 2 over square root of 5, and the last entry is 18 over square root of 70. And then the third and last step, so step 3, we are going to look at the second column, so that's now become 9 over square root of 14 minus 1 over square root of 5 and 1 over square root of 70. So that is the second column of this matrix. That is almost an upper triangular form. The only thing that spoils it is this entry here, so we would like this entry to be 0, and we're going to do that using, again, a Givens rotation, and then a Givens rotation that doesn't change this 9 over square root of 14, but is a rotation in the 2, 3 plane. So basically we're going to create a 0 here, and we have to change then this entry to make sure that we get a new vector that has the same length. So that means that we are going to construct a G3 rotation that doesn't touch the first entry, so that still is 9 over square root of 14. We want a 0 here. And then the entry that we should have here is the square root of 1 over 5 plus 1 over 70. Because then the two vectors have the same length. And of course you can write that a little bit simpler, because the square root of 1 over 5 plus the square root of 1 over 70. So this is the same as 9 over square root 14. I just copy. If you simplify this, you would find the square root of 3 over the square root of 14 and 0. And then the last step is that we are going to pick a G3, and G3 has the form. It's going to be a rotation in the 2, 3 plane, so it has this form. And the requirement is that if you multiply that vector that we had, oh, sorry, that's the new one I wrote down, shouldn't do that, minus 1 over square root of 5, and the last one is 1 over square root of 70 equals, so 9 over square root of 14, a 0 here, and this entry becomes square root of 3, square root of 14, like this. So if you compute that, you will find that C should equal minus square root 14 over 15, and S should be 1 over the square root of 15. And indeed you see that C squared plus S squared equals 1. Then finally, if you would now compute G3, G2, G1a, you will find an upper triangular matrix. So what you find is square root of 14, 0, 0 by construction. The second column we can also easily write down. And if you would compute what you get in the last column, this is going to be pretty ugly. You get 8 over the square root of 14. This entry, if you would compute it, you would get, let me see, I wrote it down here, minus square root of 2 over square root of 21. And the last entry here is going to be minus 4 over the square root of 3. So hopefully I didn't make any mistakes there, but you know the principle, and that is what is important here. Of course, normally you would never do these computations by hand. It is just to illustrate how this procedure works, and you would always do this on a computer. So to wrap up this video, what have we seen? We have seen that you can use a givens rotation to create 1 0 in a matrix, and we have also seen how to choose them to get a matrix into upper triangular form. And if you do that using a number of givens rotations, you can find the QR decomposition of the matrix. So that concludes this video. Let me know if everything was clear or not, and I'll try to improve it. And I hope to see you in the next video.